this one now. It's just incredibly slow. Okay. So, S&C, obviously, in the long distance pass, we had bullheads, switches and crossings. Round about the Second World War, that changed to flat bottom at different times in various parts of the country. We had the inclined 109, 110 pound, which changed to 113 pound in the early 1970s. The change to 113 pound went to vertical. It's basically done to reduce the number of base plate component requirements. So it was round about 800, went down to roughly 300 base plates, because if you lose the inclination, all the different variations of patterns significantly reduces. And we also went down to 1432 gauge at that time. That progressed through. It got rebranded fairly recently as NR60 56V, the 56 being the metric version of 113, so it's 113 pounds per yard or 56 kilograms per metre. So its modern name is NR56V. However, in the early noughties, RT60 was developed, so RT being rail track, so RT60 S&C, in an attempt to align with technical interoperability standards, European standards. So we went back to 1435 gauge, inclined rail. We tightened the radii and went from a 90mm cant deficiency to 110mm deficiency. We introduced transitioned switch planing at the switch toes, and we went to E++ clips. That didn't work for various reasons, which I think I'm going to talk about in a couple of slides' time. But in 2017, we then progressed onto NR60 Mark II, which partly reverted back, particularly from a geometry perspective, back to similar radii to the original 113 pound range, so that the S&C sizes were similar size, which reduces the OLE alterations when you do have to do a renewal.
Your question mark's right, by the way, there, when you say Shipley was the first one, guys in Junction.
Yes.
I remember going out there to see it. Because we were getting one.
So RT60 so was to encompass TSI compliance. One of the problems with RT60 was Network Rail left the supply chain to do all the development. So all the four main suppliers, so Balfour Beatties, VAE in Edinburgh, Edgar Allen's and Chorus Cogefer, all producing a different version of the rail fixing arrangement, different castings, different footprint layouts, and it was all a bit of a mess. And there was a very, very different combination of the way that, particularly the way the rail was clipped down. So from Balfour Beatty having piggybacked base plate, so pandrel clip holding down a base plate, which then another pandrel clip to hold down the rail with a massive construction depth. Chorus Cogefer just put a simple housing, one slightly higher than the other, and they put an inclined pad under the rail to get the rail inclination, which was quite neat. But obviously an inclined pad is softer on the outside than the inside, so there were issues with that. So anyway, we had four different component ranges, which was a nightmare. The tighter radii reduced passenger comfort. Obviously, the greater cant deficiency wasn't as good, the passenger comfort decreased. And the transition toe entry was a complete failure. So I think it was John Morgan was asked by Jeff South, probably at the time, or was it David Ventry at the time, to produce a better entry geometry to reduce the amount of jerk going into the switch toes. So instead of having a planing radius with a fairly steep entry angle, they put a transition geometry in at the toes, which moved the contact point of the flange of the wheel to the rail further into the switch to where you had more steel in the head of the rail, which worked wonderfully in the facing direction. What they forgot to do was model it in the trailing direction. So instead of the flange of the rail now hitting the stock rail with a little bit of an entry angle, it was hitting the really fine milled element at the switch toes and absolutely shredded the switches in the trailing direction. So there was the exit from Northampton down goods loop was getting renewed every 6 months. It was getting absolutely shredded. So a little bit of a failure. So and pushed up renewals costs significantly. So with the geometry being different, every time you renewed a junction with a like-for-like speed, the S&C became a lot smaller because we had tighter radii, and then all the OLE, we had to put new OLE masts up and change all the registrations. So it pushed up renewals costs. Getting ahead of myself slightly. We didn't have, so NR60 Mark II. So we want to reduce the cost of S&C renewals by matching the geometries. We want a single reference design for everybody, so interchangeability between manufacturers. Network Rail owning the intellectual property rights and having a proper REPW standard drawing range, drawing set for the full range. There was extensive modelling done of the wheel rail interface, particularly around crossings, as to get a better transition of the wheel through the crossing. So whereas the 113A range, the head of the castings were often perfectly flat, didn't allow for the 1 in 20 inclination within the wheel, so you got fairly poor ride. And the greater hammer that you got over the switch nose obviously meant that it deteriorated a lot quicker. So as part of the development, not only did we change the geometry, we changed back, we had basically 113A geometry, tweaked slightly with 1060E2 rail, changed planing on the switches, but the most important thing was the method by which the rails are held down. So we went to Vossloh, although that trial that's on the photograph on there is actually still E-clip. So this is the Vossloh clip version. That was the other trial that was done with E-clips, mandrel E-clips. This time there was quite a lot of extensive development done. So point operating equipment, there's a new Mark III in-bearer clamp lock was developed at the same time. So to improve maintainability, improve performance reliability, and have some headroom on the point operating equipment from a failure perspective. So the photograph on the right was a set of switches installed with 8 inches of cant, which are the various elements to it to try and force it to fail. So how badly can you set them up and it still work? So a good amount of headroom for it to be wrong and still operate. So various things, even pouring coal dust into the point operating equipment, does it still work? So they actually put quite a lot of effort into developing something that was more reliable than what we had previously. So back to tangential geometry, 1060E2 rail, 1432 gauge, I've been reading to myself here, inclined rail, Mark III clamp locks, Vossloh fastenings. I'm still not certain myself why we went to Vossloh fastenings. It was partly due to a cost because they were deemed to be cheaper than Pandrels until they adopted them, and then they put the price up, so just as expensive as the Pandrel clips. We've got a mix of base plates and direct fix, better crossing design, switches as well, but mainly crossing design, and UIC 33 checks. So for those that don't know what UIC 33 check is, it's a C trough that's about half the height of the rail. It sits on its own base plate. The point is because it's not directly attached to the running rail in the same way with a CV block in the same way a traditional 113 is. You can actually put packers in the back, so as it wears, you can actually adjust. You go out and do a maintenance adjustment of the check rail and maintain your flange way opening. Wish I had a better photo of that, but don't unfortunately. So S&C geometries are quoted in 2049 Track Design Handbook. However, there's been a bit of moratorium on updating that for about the last 15 years. Nobody dare touch it because there's so many errors in it. As soon as you open the can of worms, it's going to be a nightmare. So we've produced an REPW with a list of the geometries to then use in combination with the REPWs themselves. So full range of geometries in there. So you've got the switch information at the top, circular turnouts and transition turnouts. So turnout radius going to the origin, find the right diagram, going to the origin of the switch, and then you have a planing radius where you have a flatter radius that hits with a slight entry angle. So that's exactly the same geometry arrangement that you've got with 113A, just with slightly different radii. So if we're just zooming in a little bit in here, so it's very similar. 245 metre radius for 113, 331, 645, 980. So couple of changes they made to try and make sure that the lead lengths were very similar. The F was a FV 18.5 went to an F18, which tightened the radius slightly, and an SG 21 went to a 20 and a quarter, and also the G from a 24 to a 23.5. So we have gone for a slightly tighter radius. So when I said about 90 mil cant efficiency, which is what all 113A units are rated about, the higher speed ones that they've tweaked are all set at 95 mil cant efficiency, which I think is actually on the next slide. Yeah, so 96 mil. So most of the range is at 90, exactly matching 113, but some have gone to slightly higher. So, Mark, 1060 rail were allowed 110 mil cant efficiency. We're still allowed 110 mil cant efficiency. But one thing that does is it breaks the Euro norm for having 100 mil abrupt change in efficiency at the switch toes. So dropping down below 100 gets us compliant with the Euro norms, but it also allows us to flex a turnout. So if a turnout's already designed at the limit, as soon as you do a contraflecture semiflecture turnout, turnout off the inside of the curve, you immediately then have to jump one up in the range. Whereas if it's designed at 90 mil, but you're allowed to have it at 110 mil, you can flex it to a certain extent with the same unit before you then have to step one up in the range. So it allows a little bit of flexibility and a full set of REPWs to accompany the new range. So anyone know where that is? It is still there, and it's still a double junction.
Yeah. So on what's now like to call the Northumberland line?
Yeah, it's on the Blythe branch. It's winning junction.
Yeah,
Just on there.
It's on the Northumberland line.
So
Lies and time.
that's my dad's photograph from 1956. I think that one.
Oh, it's still there.
The box is still there, although the swinging gates have gone, I think, with the big.
Oh, yeah, that's right. It's got the barriers in.
So R60 Mark II double junction. So we started developing the range back in 2017 for very specific purposes. From my perspective, it's because we needed it for a Ravensthorpe junction on transparent route upgrade. In 2018, we did quite a fair amount of cross-industry consultation. We had a working group in London back in November of 2018 where we discussed a lot of the things that I'm presenting here. So the cant efficiencies we're going to use, geometries, what do we match, what do we try and enhance, so arrangements in there. And then it kind of went on pause because there was no money towards the end of the control period, and we've actually restarted back in November at the end of last year, 2024. God, 2014, we're behind. So we have development now in the current development budget in the current control period. So the intention is to carry on developing it and produce a proper set of REPWs and publish the geometries that I'm about to show you in a few minutes. Because if the geometries are not out there, designers at feasibility and development stages don't know what they can design. If they don't know what they can design, they either don't do it or they make up their own version, which is probably just as bad. So some limiting rules, some examples of what we're looking at. So double junctions are now classed as complex S&C, which means that it contradicts itself within standards. So it says a complex S&C, you can't have any, what's that one? What's on there now? So that's the amount of cants you can put, I think. Yeah, counting complex S&C 0, but fixed obtuse crossing, which is a double junction, you're allowed 110. So the fact that we slotted in there, it actually contradicts itself, and there's quite a few contradictions in there. Quite a few elements that are just wrong as well. So is it really appropriate to have a cant gradient through a switch diamond of every bit of track going? That's probably the worst place to put it. Again, the amount of cant on the through leg, double junction or complex S&C, we're now limited to 50 millimetres of cant on the through leg through a switch diamond. Well, if you're allowed 90 mil on the turnout leg, why are you restricted to 50 mil on the through leg? So again, just grouping it in with complex S&C, the likes of scissors and double slips and other really complicated bits of S&C, they're kind of restricting it, and the standards need to be written a little bit better than they are. So obtuse crossings, fixed obtuse crossings remain at 75 mil cant efficiency. We propose not to change anything. Only instead of 110, although we've got NR60 S&C, we're going to stick to the 90 mil cant efficiency arrangement from 130. Couple of reasons for that. The best wood in the world, it doesn't matter how well you manufacture it and install it, there's always going to be a minor geometric discontinuity as you go through the obtuse crossing. So just to have that little bit of headroom from a cant efficiency perspective kind of just leaves you that little bit to play with, a little bit of a comfort zone there. So that's no prizes for guessing that one.
It's making you trouble, right?
So the range of geometries are now complete. We're intending moving to produce a full suite of REPWs with all the appropriate range, which we didn't have at all with the Mark 1 version of the range or the RT60 version of the double junction range. And we're looking at geometries that are like for like, and also enhancement versions, which I'll talk through in a little bit more detail, but trying to get the most out of double junction. So at the double junction, I might refer to N1, N2, N3, and N4 crossings. So the N3 is the obtuse crossing in the middle. So standard double junction, or a back-to-back double junction, or a three-line crossover. So that's another element that we've been looking at, which has never ever had an REPW that I'm aware of, or a set of defined geometries for certain speeds. So some of the math in 2049, here the maths are wrong. Some of it are just completely wrong, and then, as we know, a lot of it is just ever so slight simplification, so it's there or thereabouts. But when it comes to doing in CAD to 20 decimal places of a millimetre, then you do actually need the correct numbers. So a lot of the calcs and geometries that we've done, we've recalculated from first principles. But one of the key elements that we have changed is its centreline intersection. So the angle, crossing angle, is at the intersection of the centre line. So with the old range, the 113A range, each half was done separately. So if that was an 8 crossing, 9 1/4 crossing, it'd be to an 8 there, and you do the other half from a 9 1/4 or whatever it was, 7 back to an 8. So each half was done separately. You actually had a bearing discontinuity. It wasn't a tangential geometry through the turnout leg. It was a bit of a fudge, which CAD cannot cope with because it's not continuous geometry. So we're going for centerline geometry for the obtuse. So the angle is actually at the crossing. So if that was a 1 in 8, that would be a 1.805, and that'd be a 7.95 on the inside. And given the modern manufacturing techniques for crossings and the milling of the crossings, it's easy to accommodate that subtle change in the angle. Some quotes from standards. Actually, not going to go through these because most of what's in the standards are either misleading or wrong. So when we're developing the ranges, the enhanced versions that I'm going to talk through in a moment, what crossing angles can we use? Do we stick to exact standards, so a crossing angle that we already have? Do we come up with new crossing angles but do them to quarters, which is traditionally what we would do? Or do you start going to decimals, 0.1 or to multiple decimal places? And you'll see why that's important in a moment. So the Mark 1 range just went straight for a continuous radius all the way through, and the crossings were what they were, so to 3 decimal places. Similarly, although generically we have quarter angle crossings, a HV 30.365 is still a decimal crossing. It didn't work with a standard a rounded crossing angle, so we have actually got precedence of using more unique angles. So that's the full 113A range of double junctions. So that's quite a large range. So we looked at which ones do we directly match. So the ones that are struck through are ones that we decided not to replicate. There's quite a lot of increments in there, so we took out the ones that were probably least likely to be used. If somebody does need them, because it's a like-for-like renewal, we can always reintroduce and add one to the range at a later date. But the numbers down the right-hand side is the overall lead length from the first switch to the very last M4 crossing. So there's very, very little difference in lead length between the 113A version and our NR60 Mark II version. So it's 10 millimetres longer for a B double junction, 18 millimetres longer if you go to a D. 400 mil longer for an E. These are shorter, the higher range are shorter. If I remember, I said the turnout side will have a steeper angled crossing, meant that the whole double junction becomes a bit shorter as a result of that. So the faster double junctions are actually slightly shorter. I mentioned about 90 millimetres for switch diamonds and 75 mil for fixed obtuses. I will touch on both switch diamonds and where we should be using them, and problems with fixed obtuse crossings in a couple of minutes. So, apologies for flicking through some of these, but so when it comes to an enhancement or trying to increase the speed of a double junction. How a double junction fits within a fixed constraint is usually the angle of the last crossing and what happens afterwards on the diverging line, as opposed to the size of the junction itself. So we've actually developed a series of more aggressive range, extra option in the range where we have more aggressive angles and tighter radii through, which gives us some opportunities for enhancements. So an R60 Mark II B double junction, so this is mentioned about going to decimals. So if you go to 7.6, 6.45, 4.8, 4.1 is a B double junction fit for 20 mile an hour, which the last angle is almost the same as the equivalent AV double junction. So down in London, we've got AVs and BVs everywhere, and we're not supposed to have those in running lines anymore. So it gives us the opportunity to get from an A switch to a B switch, or from a B switch to a C switch. So having enhancement versions that allows you to do that, and using the geometry to its maximum capability by going to decimal crossings helps. So there's a diagram here that helps to demonstrate that. So the black dotted line on here is an AV double junction, and then what happens if you continue the radius beyond the crossing. The version that we've gone for is actually the light blue. So this is a B, so AV double junction or an NR60 Mark II B double junction is almost the same. See, the blue line is very, very close. So it means you can actually upgrade junctions, get a line speed increase, but more importantly, get rid of that A switch and at least upgrade it to a B in the process. So a different version, going from a B to a C, same again, not quite as close, but the black line to the blue line. Count deficiency diagrams. I love count deficiency diagrams. So 90 mil count deficiency. So a B switch at 20 mile an hour is actually only 68 millimeters count deficiency. So if we push that to its limit, so we keep our B switch panel, but at the heel of the switch we go to a tighter radius. So instead of an 8, we now got 7.6. We get it up to 90 mil deficiency and continue that all the way through, which only works if you've got switch down. But I'll come back to that. But it makes it more aggressive. It's utilising the rules to its maximum. Similarly for a C switch, so we've got C8 3/4 instead of a C9 1/4, and then all the way through. It becomes more apparent with the D switches because the count deficiency, sticking to standard angles, the count deficiency drops off all the way through. So you're not getting anywhere near as steep a crossing angle by the end. So this keeps moving forward. This is just diagram, that's it. So that's our new range. It's actually changed slightly. This is one version out of date. But I mentioned it in enhancement ranges. So everything on there is a like-for-like renewal, with the exception of the top ones from each range. So the top B, the top C, the top D, E, F, G, S, G, and G, round on a H. That's the more aggressive version that allows you to do enhancements. So we've got a like-for-like range, and then everyone in the range has an enhancement version where we can use to get line speed increases. So I'll guess where that one is. Give you a clue, it's on my project, current project.
Micklefield.
Yes. So even though we're developing an R60 Mark II double junction size, that's the old A1 bridge, I think. We ended up renewing that in 113A, even though we were developing Mark II junction, which was a little bit frustrating, but it's fine. So, where should we be using double junctions and why? So, there's various comments in standards saying we shouldn't be using double junctions, or more importantly, shouldn't be using obtuse crossings. So, there are good reasons why fixed common obtuse crossings are a maintenance liability because they crack and fail, and there are reasons why switch diamonds are a maintenance liability because you keep losing point detection. So there are various comments in the standards in 2049 that should dissuade you from using them. So very recently, so this was 2 months ago, apparent Eastern Region crossing strategy picks up on various crossing failures. So and these are fairly common, and most of these failures are in the same place on the crossing. So there's various failures where the crossings get small crack and it propagates and goes all the way through the crossing very quickly. Funny enough, all these are common crossings, but then at the end of it, they state, well, we shouldn't be using obtuse crossings when all the failures are getting in common crossings. The failure mechanism is exactly the same and can happen in obtuse crossing, but they're using an excuse to then try and put more pressure on not using on crossing. So we've got here short term, fix the problems, long term, stop having diamonds, which isn't the solution. The solution is fix the problem. If crossings are failing, you need better crossings, and there's lots of known reasons why crossings fail, and they are actually attempting to fix those. So we all know where your crossing is. That one will be a harder one for everyone to guess. I'm just covering that up. That's Great Western Junction at Basingstoke. So particularly, those are both mine, and they're both terrible, but they were forced for a like. So that's a 1 in 4.5 crossing on the Southampton main line, 100-mile-an-hour line speeds with 32 axle loads. It's an absolute nightmare, that crossing. It gets so much hammer. The first crossings that went in lasted 2 years and they failed. They remodelled the support arrangement, which I think is in the photo in there. So put an extra bearer in with 488 mil centres instead of 650 to provide better support for the obtuse crossing. That went in 10 years ago and is lasting okay as it stands at the moment. So there are various issues with crossings. The lugs for the clips, so keeping a constant foot geometry of having the wider foot all the way through, reduces all the little angles at the propagation point for cracks. Also, the crossings are designed with a minimum amount of steel in them to make them as cheap and as light as possible, not to be as robust as possible. So they're putting more steel in the foot and also putting the continuous lug down the side. Also, milling crossings out of a single billet of steel. So that's a trial that's gone in at Chesterfield. It's only been in 3 years, but apparently that's managing very well. But again, the more steel in there, the more robust it is. So that crossing is about 3 times the cost of a normal cast crossing. Normal cast crossing is somewhere in the £25,000 range. That's 75 grand. But it'll cost you hundreds of thousands of pounds to put the thing in. It'll be 100 grand probably to go and replace the crossing. So it's more, if it lasts 5 years longer, it's more than paid for itself as a whole life cost, because it isn't the cost of the materials that the big issue. That's about 10% of the overall cost of a normal renewal. It's the materials. It's actually the cost of putting it in. So
Who makes them?
I don't actually know who makes them. But they were talking about potentially using art for emergency spares, so having a set of digital patterns for crossings for like renewals, because in theory, get a billet of steel, chuck it on a milling machine, you can have one turned out within a day instead of having to wait three months for somebody to go and make a mould or go and get one cast. So they are actually talking about using them for unique crossings or specials, and when you need a really quick maintenance replacement for something that's not particularly standard or that is flexed. Right, so obtuse crossings are banned above 110 mile an hour, although I wouldn't even fancy putting, well, Great Western Junction's 100 mile an hour and it's an absolute nightmare. You can't have fixed obtuses above flatter than 1 in 8, although 1 in 7.5 is probably the sensible limit. There's various other rules on there that I'm not going to go through. So, the challenge is, we historically don't like double junctions. Fixed obtuse crossings fail, switch diamonds, lose point detection, and you get the failure because of the signalling failure. So the challenge is, if it's broken, fix it. Don't avoid using it, which is the whole point of the development that we're going through now. So to tackle the reliability issues, specifically with switch diamonds, but also with the fixed obtuse crossings, and produce better arrangements that last longer and sort out these issues. There's quite a common phrase that's used about putting passengers first. And that can be used in various ways, usually about not disrupting services when you're doing engineering work. But passenger comfort is just as important from putting passengers first. Who wants to go across a ladder of S&C for an opened out junction as opposed to a conventional double junction with a switch diamond or fixed obtuse has a constant or each cant deficiency all the way through, and it's far nicer a ride and from a passenger comfort perspective. Less changing of direction actually mean less wear and tear for the track. It's not the track engineer that doesn't like switch diamonds, it's the signalling engineer, so let's go and have a decent battle with them. Switch diamonds are actually arguably lower maintenance than a fixed obtuse, but we constantly pushed into fixed obtuse crossings. So, size of double junctions. 25-mile-an-hour up and down double junction takes up the same space and the same footprint as a 50-mile-an-hour conventional double junction. If you then separate the turnout from the crossing by having at least 20 metres of plane line between the last through bearers and separate that even further, a 25 up and down double junction is the equivalent of 70 miles an hour switch diamond double junction. So from a line speed perspective, opening out a double junction, not only does it require a greater land take, so your formation is wider, it also doesn't fit. So you are really constraining yourself from an enhancement perspective. So this is where a lot of the challenge that I'm throwing in is not necessarily for maintainability. You need to do the best you can from an outputs perspective and journey time and speed, but deal with the maintenance issues, but still try and achieve whatever you can. So what's the value of a second? So increase in line speed from 25 mile an hour. So if you 25 to 50. So if you have that junction currently and you renew it back as a conventional double junction, get it to 50 miles an hour. You save between 30 and 60 seconds of journey time, depending what's happening around it. That has between 25 and 100 million pounds with the business case. So the value of a second on transfer and rail upgrade, the value of a second is somewhere between 1 and 3 million pounds. So if it's less than, if the cost of an intervention is less than £1 million, it's an absolute no-brainer. If it's between 1 and 3, you investigate it. If it's above 3, you forget about it. So somewhere between 1 and 3, depending where you are on the route and the number of trains, 1 and 3 million pounds per second. So if you're saving 60 seconds, at least 60 million pounds of the benefit. So 60 million pounds of the benefit, that covers a lot of delay costs, even if you do install something that doesn't work properly. So if you install an old double junction that fails regularly, 60 million quid is a hell of a lot of delay costs. So when you look at the bigger picture and the economic benefit of getting trains to the destination faster, there's still a big push. We should be pushing getting everything we can out of the network. So little case study. That's Daily Bridge. So that's the fixed up tubes 1 in 7.5 that went in. Roughly 18 months ago. So that's the original layout. 25 mile an hour up and down junction there, so crossover and lead. The remit was to get that up to 50 miles an hour, so we need to upgrade that. So if we were to do that as an up and down junction at 50 miles an hour, it looks something like that. So at Staley Bridge, there's a very aggressive elevation difference between the two routes, straight off the back of the diamond crossing in here, right, just there. So doing this extensive earthworks, the gradients didn't work. You need a new bridge. You take out a couple of houses. So you literally can't. It's not sensible to implement a scheme like that that was pushing 50 to 100 million pounds to do that. So instead of an up down double junction, if we put a switch down double junction in, I mentioned earlier, 25 fits, same as a 50 mile an hour switch down junction, fits wonderfully on the footprint of the existing railway. That would have worked. LNW signalling maintenance lead steadfastly refused to accept a new extra switch diamond in his layout. And I've never had somebody full on swear at me in a meeting before to that extent, other than possibly John. So absolutely steadfastly refused to do that. So the consequence of that is we needed to open out the track interval so you could continue the radius and get the crossing angle flatter than 1 in 8, so 1 in 7.5. So we managed to do that, but that now meant remodelling all this extra part of the layout. So we added about 20 million pounds to the scheme to accommodate not putting a switch diamond in the layout. And that was one person insisting on not having a switch diamond. So trying to put it in a bit of context as to where the value is. One person doesn't like a little bit of extra cost. Whereas the value you get out of it. So another challenge is you need to renew. So the LE crossing strategy that I pulled up a couple of minutes ago, some extracts in there, suggested the long-term strategy is start opening out junctions. So instead of spending £50,000 more on a crossing to stop it failing, you want to spend several millions of pounds of opening out a junction instead. Where is the value? It's people thinking, I need to save money on my part, but actually the consequence is like 20 times more expensive. We come across that so much. So this was a very good example. Not having a switch diamond and the potential performance issue and cost to Network Rail maintenance of that compared to spending £20 million on a project to avoid using one. And ironically, the changing remit on TRU of 15 extra freight trains a day. We've now got intermodal containers going over this fixed obtuse crossing, which will probably now fail very, very quickly as a result, where a switch diamond would have been pretty robust. So that's a photograph of the rest of the junction, the diamond being in the background, but the point being of having to remodel all of this to accommodate the fixed obtuse. So these are not my slides, these are pinched from Matt Crompton, who's from Milton Keynes, headquarters in Milton Keynes, who developed a lot of the detail behind all of this. So I'm not actually going to mention some of these, I don't understand them, but I'll get on to the case studies. Right, so failure mechanisms for a switch diamond. So when it's cold, everything contracts. So you've got stock rail runs all the way through, and then you've got switch rails which don't connect to anything that loose. So in cold weather, everything contracts, the gauge spreads. You lose frame detection for the points detection. So a slight animation of it. Similarly, in hot weather, everything expands and you lose gauge. It gets tight. So you also lose points detection. So in addition to the stock rail moving and the gauge moving, which is the main mechanism for a points failure, you've also got the creep of the switch rail. So the switch rail itself is obviously held at the heel, but the switch is loose. Everything else is stressed, so it can't move, but the switch rail can. As it gets hotter, it lengthens. The switch rail can easily get 10 to 20 millimeters longer in extreme hot weather. Now, on a normal turnout with a very, very fine entry angle, it doesn't make a lot of difference for gauge. But with a quite a steep 1 in 8 angle, you will push that switch rail up 20 millimeters. Again, the switch rails come in and you get tight gauge again. So that's the other mechanism. So two things we needed to fix, or main things we need to fix. One is stop the gauge spreading, and the other one is to allow the switch rail to pass through the point operating equipment, slide through it without pulling it all out of square and causing a points failure. So I mentioned all the development earlier that we did with turnouts. We've done something similar with switch diamonds. We've now got several in track, even though we haven't actually produced any of our APWs yet. So Uddingston, just south of Glasgow on the West Coast Main Line. That was actually the first one to go in. So that's similar to Colne Junction, but it's a right hand instead of an equal set junction. So it's 90 miles an hour, right hand 90 mile an hour junction. And that's the switch diamond element in the middle with long bracing rails on the outside. So slightly different arrangement for different angles of crossings. And I think as we've gone on, we've come up with a slightly more robust version. So the strap rails are just clipped to the end of the bearer in that scenario. You see it's slightly different on some of the later versions. So that's a 1 in 21 switch diamond. That's its join, that long junction. That's the first fixed obtuse crossing, so a very, very tight radius curve. That's about 150 metre radius at Falcon Junction, just round Clapham area, somewhere around there, south of the Thames. Our APW again. So in this case, it's a full head rail on its sides, strapped to the rail, so slightly lower tech. So that's not necessarily taking any, because it's a cast crossing, it's not taking any lateral bending loads, it's just trying to keep the bearers in the correct positions. 3-line crossovers, Ballon Junctions, that's another one that's gone in there. So we've got the geometries for that. That's its drawing. This one is Deptford Hall, which is just north of Milton Keynes. No, Bletchley, sorry. Associated with East West Rail, I think is where the East West Rail route comes back onto the main line. So you notice now we've got the strap rails clipped down, but we've also got heel blocks onto the running rails. So that effectively creates a big Viridale girder in there. There's absolutely no way that's moving at all. The disadvantage of that is that the blocks are in the bay. So if you're going to tamp it, you're going to have to take the strap rails off. So you get some benefits, but also in some ways it makes it harder. But all the point operating equipment is out of the base. You haven't got any stretcher bars or point operating equipment in the base. So you can tamp it properly through the centre of the obtuse. Again, that's its drawing. Staley Bridge that I mentioned a couple of minutes ago, so that's a 7.5 fixed obtuse. Raised check at the knuckle proved a little bit of a challenge. So you're not allowed to raise check rails because you can't run rail skates to recover failed trains. So we've got a nice little ramp on the end. Can't see it very well. And it's not flat enough really, but a little ramp on the end so you can literally drag a skate over the top of the raised check over the obtuse. This particular layout, you can actually get a route around running wrong road. You can actually get around the obtuse if you needed to, whereas obviously some locations it's the only route through. So a little bit of an issue. I can't remember the exact reasons, but a very flat obtuse does need a race check for wheel transfer management. That was the drawing. Testing again, similar process. I don't think they put this on 8 inches of count like they did with the turnout and tested it there, but again, tested it in different scenarios, deliberately pushed the switches out of square. Does it fail? And checking various different scenarios. Point operating equipment, this has a unique version. All the main suppliers weren't interested in doing really low volume switch diamonds, so we've ended up with a Unistar point operating equipment, which is working really well. It does the job, but again, the signaling maintainer doesn't like it because it's not what they're used to. So they'll have to go on a training course for how to install or how to maintain a Unistar point machine. Cropping designs, just producing better crossing design, basically, just designing out the failure mechanisms for the cast crossings that we have and just making them more reliable. I've already mentioned a lot of what's on there, so getting POE out of beds. Full depth or shallow depth, we've gone for shallow depth switches. To match turnouts. However, there are consequences of that. A shallow depth switch is far stiffer, it's far more difficult to bend, and switch diamonds are often fairly short, movable length, so it does create issues. 1 in 8 is the practical minimum of sharpest radius we can go to with a switch diamond with the design we currently have, keeping everything fully welded. To go sharper, that will probably mean having the switch rail fish plated or tight jointed onto the end of the casting, because everything gets a lot closer in a confined space, which a lot of people are saying you can't possibly tight joint it, but compared to putting a fixed obtuse in that will fail regularly, I'd still go for a switch diamond personally, particularly for a very heavy axle load area or high speed area, or combination of the two. I mentioned Unistar inverter system. Thermal decoupling of the switch, so the mounting for the point drive actually it's slotted, so the holes, and it's set up so that it will actually slide through the point operating equipment to reduce the failure mechanisms that are there. So we reckon we've solved about 95% of the problems that we had from a performance perspective from point operating equipment and failure scenario. So. Feedback, generally very good. Everything that's gone in is performing very well to date. A couple of initial niggles, generally by them not being installed properly in the first place, or not being maintained. So most things, once they're installed, they need a follow grind fairly quickly after installation. So the one at Denby Hall didn't get that, and had some strange wear patterns as a result. So from an enhancements background, we need to make the most out of our renewals. Trans-Pennine Route Upgrade is now an £11 billion programme. It's a ridiculous amount of money. There's now no money for anything else. The renewals budget, I think we're down to 4 junctions a year at the moment. We've got no budget left for renewals. However, renewals are where the efficiency are. Instead of doing big projects, let's make the most out of a renewal when we do it. If you just piecemeal, have a master plan and piecemeal, increase the speed of junctions, particularly double junctions, as you go. If you're already there doing the renewal, the enhancement is relatively cheap compared to going there as a standalone project. And renewals tend to do everything a lot cheaper than major projects anyway. So let's make the most out of it. We need to think about the balance between capacity, performance and maintenance, but we don't think about the output. So one thing I have learned from the projects that I've been on is everything has an economic value. You need to think of anything. If you're trying to sell anything to the Department for Transport now, you've got to say what's the business case associated with it. What is the economic value of a line speed increase? And interestingly, if you can get a line speed increase, we strap for cash for renewal. If you can do an enhancement, you can get a little bit more money than you actually need for the enhancement, so it actually partly pays for the enhancement, or sorry, the renewal, or the materials you use on the renewal, you can put in better materials. So the challenge at the moment, we're actually starting to renew it back in 113A again, or NR56, because the strap for cash, whereas an R60 Mark II turnout generically lasts 50%, if not 100% longer than a 113A unit, and under bearer pads and everything else. We're starting to strip things back from a capex cost perspective, but the whole life cost is significantly worse. So enhancements, if we can combine enhancements with renewals, it does actually help the renewal. So we've mentioned fix the S&T problems. So hopefully we can persuade our signalling colleagues to let us put more switch diamonds in. And that's about it. So although I've been doing a lot of talking here, it was the geometries was my baby, but all the technical element of the point operating equipment, the profiles of the crossings, everything are all Milton Keynes and the Network Rail team down there. So just a quick shout there, and particularly that some of the slides are actually theirs, not mine as well. So that's it from me.
Okay, thanks, James. Brilliant.
So it's worth warning everyone that this meeting is actually the first one that's getting recorded and will probably get published. So
Yeah.
polite questions, please.
Yes, no swearing. There's a lot of food for thought, so I'll open it up. I'm sure you're open to
Yes, absolutely.
some questions from us all. Anybody got any questions?
I've got one. My name's Glenn Melvin. I'm a principal engineer for the permanent way at Nexus Metro, small system, and we have a double junction, but we are NR56. And looking at the great presentation, but looking at the slides, and I'm talking about NR56 here. There's still, that last sentence there: countless designers, contractors, trainers, manufacturers, and testers, etc. I still see a lot of S&C going in, which is base plated on concrete bearers, and that kind of puzzles me, because I mean, obviously, I get why you need the base plate in the NR60, because it's inclined, but in the vertical S&C, certainly at Nexus, our strategy, our my strategy anyway, is to remove as many of those bolted or screw connections, and I still have Vossler when they've been for builds trying to convince me to put the screw Vossler butterfly tips in, and I was just wondering if you knew if there was any particular reason for that.
So the range, the vertical range, with the exception of the switches, everything is direct fixed to the bearer. The Mark II range, we do still have direct fixed, cast the inclination into the bearer. So again, we've got base plates for the switches, but because of the UIC 33 check rail requires a base plate.
Yeah.
So anywhere with a check rail also then has to have a base plate, which then means the crossing that's next to it also has to be base plated. So anywhere with a check rail and the switches are base plated, everything else, even though it's Vossler, are actually direct fix.
Mm-hmm. Right.
So they have maximised direct fix where they can. And similarly with 56 range, 113A range, that's as maximum as you're going to get, because obviously you need base plates for the switches, but everything else is direct fix if you go on concrete.
Any help?
The second part to that, if that's all right.
Sort of roll.
The NR60. I mean, we'll never put in 60 kilo rail on a metro system, but and I see it all on concrete bearers. Have you installed any on composite bearers yet?
So, FFU and composite bearers are approved for Network Rail for use for plain line sleepers, but not for S&C yet, because there's still concerns about thermal expansion engaged. They are trialling it at the moment. Interestingly, there are a few locations where it will probably be better. So, Newer Crossing was renewed with FFU
I've seen that,
about 5 years ago now. Interestingly, Whitehall Diamonds might be getting FFU bearers underneath the crossing. So one of the advantages of FFU is you could actually create a frame sleeper, so where you've got a piece that actually runs underneath the casting as well. So it's a big H basically. If you could do that and provide continuous support under the crossing, the better supported the crossing is, the less likely it is to fail. And with it being FFU, you can do it to whatever shape you want. So if there's nothing sticking out beyond the rail, it's just literally supporting it vertically. From a tamping perspective, it looks like a normal set of sleepers, so you can still run a tamper through it. And then the longitudinal bits, you just can go row bell bit of that, squeeze it a little bit extra. I've got tampers that can squeeze both ways, but that becomes a bit difficult. So there are options of providing far better support for crossings by providing longitudinal support as well as your perpendicular support. it's a bit too left field for a lot of route asset managers. Though, that one.
Thank you.
Just going back to the geometry, James, I presume the switch doors are square on it.
Yes.
Yeah. Going back to your picture in of Ashington, I think that well in the Ashington area. I remember Jeff Wheatley back in the day. Jeff came up from the southern region, and obviously the bearer spacing arrangement, which we didn't touch on very much, was a bit more complicated with Bullhead and S&C. He actually offset the we actually offset the gauge or the toes by half a gauge, half a sleeper spacing.
Much of that. I know it was fairly standard practice on Bullhead to stagger them slightly to make sure you get your gauge on your turnout leg.
Yeah, but yeah, smashing presentation. Thank you.
Any consideration? Sorry, go ahead.
Yeah, I think we're down at Nexus, so I'm a project manager at renewals. Thank you for the presentation. The fluency which you use all this terminology is quite staggering, if you ask me.
I always give any acronyms. I
Not
apologise.
necessarily from a technical background. The point I'm interested in is more the how that one person essentially could have that clout and stipulate that they weren't, happy with that initial decision and then increase the cost. What time stage did that happen? Outline design, detailed design. How was that? How does the government?
That was between grip 3 and grip 4, which is now ES3 and ES4. So between the option selection and outline design. So it was more or less at the option selection stage of what layout we were going to put in. Unfortunately, it's very easy for people to say no within that URL and introduce lots of cost that is inappropriate. People won't accept risk. So challenging something becomes quite, challenging people having personal preference is quite difficult at times. And it requires the right people to be on board, which potentially goes up to a route director to say, no, we are doing it this way.
And did it get to that stage?
No, it didn't go that far. It was that robust an objection that we actually gave up, which to a certain extent I regret because I don't usually give up.
No, thank you.
Was he died in the wool? Well, I mean, was he a newbie on the block?
Oh no, he's died in the wool. I won't mention his name, but
From Midland region.
no, he's from Manchester.
There you go. Against an Eastern region designer.
Yeah.
Get me back. Yeah. Anybody else?
Has Miller Hill been renewed, James?
No idea.
No idea. That one was an interesting one. I did some work on that about 15 years ago. The straight alignment runs into Miller Hill Yard, but the main line, the East Coast main line, was on a 95 mil cant, or 95 mile an hour, I can't remember. But that would come into the category of a crossover and single turnout with a bit of land purchase over the thought.
If speed is of absolutely no consequence, i.e. its connection to a siding, then you would absolutely open it out if there was the opportunity to do so. It's about the appropriate solution for the appropriate location. I mentioned Great Western Junction and the two diamonds that are in there. I actually pushed because I did the outline design for that. I pushed quite hard to move the junction to the other end of the station, so completely get rid of the diamonds and add an extra platform. It just stonewalled, wasn't allowed to change it because we're already through option development at that point. It still worked really well. There was space to do it. Then about 5 years ago, I spoke to the RAM and he said he never even knew that was an option. He wouldn't have accepted the switch diamond had he known there was an alternative. So it's finding the appropriate solution for the appropriate location. Now, 1 in 4.5 is too steep to have a switch diamond. If we could have had a switch diamond, it would be significantly better.
So the options cost of it. How far back is that? So is it more that we've got more pressure on the switch diamond or the obtuse in the last 10 years, 15 years?
There's a hell of a lot more higher tonnages than we used to have. They're generally getting a lot higher use than they used to. So therefore they deteriorate a lot quicker. It's flawed design to a certain extent, but these crossing designs go back to the early 1990s probably. And they're designed to be cheap, not to be robust. And that's the problem.
In the short term.
Yeah. So ironically, a really good glued, hook pinned part welded crossing is probably better than the cast crossing. So they wear quicker because they're a different steel. So they wear quicker, but they're actually easier to maintain, and they don't fall apart because it's a rolled section instead of a cast section, so it's less likely to have flaws. So it's an interesting challenge there.
Sorry, one final question, just about the figure you quoted there, about for every second you can save an astronomical amount of money. Presumably that has been substantiated or the
Yeah, that's from business Department for Transport business case. It's the second save is a big chunk of the case for Trans-Pennine Rural Grade. They're saving 15 minutes on the entire route, which equates to billions in benefits over the next 60 years.
Does that vary by region and area then? Or
It will vary based on the number of passengers more than anything, I think. So different parts of Trans-Pennine. So Leeds to Huddersfield has a much higher benefit than between Huddersfield and Staley Bridge, because the passenger numbers are significantly higher.
And I just come on there, and in the past, there was a severe usage of brake blocks on one of our local hold and things coming out of Gateshead shed doing a Trans-Pennine run. Every 2 runs, I had to change the brake blocks. Because of the braking distances and the severe speed restriction going over the Pennines, just the gradients. So
That's usually when you got to L&W is that there's been just
Across the board. I was going to ask on the switch diamonds, is there any consideration given on those strap rails that to put in rail anchors either side of the bearers to limit the movement?
So the strap rails, for the switch down, the strap rails are to provide lateral resistance, not longitudinal. Do you mean as in MF rail anchors to stop creep? They're not there for the creep element. They do perform that as well. They hold the bearers in position. But it's more about stopping that for the gauge spread. It's to provide lateral support.
But what about the running rails? Could you not put some on the running rails?
They looked at various. The trouble is, where you need the strength is where the point operating equipment is, so you're quite limited for space and what you can do. We looked at a cast knuckle with a switch that goes against that, but it was still physically tying it down to the bearer with clips, because you still got movement with clips. So it's just about making the whole system rigid rather than just the running rails.
And by adding all those strap rails, how does that affect the tamping capability? Is the tamper?
So the last version I showed you, which had all the heel blocks on, you need to remove the strap rail to tamp it.
You do
in that scenario.
Yeah, we had some nightmares on the West Coast main line trying to tamp in the Wigan area with some of the more modern stuff.
So there's different versions with and without. The longer ones don't have the longer switch. The 21 I showed you didn't have the boxing, so that is fully tampable.
Okay.
so
Yeah.
on the crossings themselves, can you actually check how the thing's moving? So like electronic method of seeing how the thing moves overall under load.
They will probably put strain gauges and accelerometers and everything else on that problem size to try and understand what's happening.
Have you done that?
They will have done. I don't know of specific cases where they've done that. But part of the problem is you don't know whether is the crossing failing because there's something wrong with the crossing, or is it poor formation? It could be poor drainage. It could be lots of reasons why crossings fail. The examples out there are just flaws in the casting, cracks propagated, and it's just gone all the way through. Obviously, some of those are quite severe when a crossing completely breaks rather than a crack being spotted and it just getting a speed restriction until you replace it. A completely broken crossing, particularly at Cornwall, 125-mile-an-hour railway, is pretty severe. So it's quite dramatic at times.
Actually, James, was about 2 or 3 months ago, the presentation from a lady from Crorail, and they all had modifications to cast crossings, which reduced the stress by about 50%. Are you sort of coordinating?
I know again that's one thing. So they are looking at the design of the crossings. So Mark II has encompassed a lot of improvements. Point is, we should retrofit that back to a direct replacement for an R56 range, so that if you get a maintenance renewal, it outwardly looks the same and it fits. It's got the same footprint for the plates and everything, but it's actually a much more robust design. So we should actually be updating. We're not yet. but we should go through a process of just updating the entire range to be more robust and take into account all the lessons that have been learned. At the moment, we're just ordering like for like replacements and getting the same old rubbish, which is a bit unfair saying the rubbish.
Good. Well, I think the amount of questions underpins the quality of the presentation tonight. So thanks, James. But I'll ask John Watson to pose the formal vote of thanks to him. Thank you.
Right. Thanks for coming down, James. Just in time arrival. Fantastic. Following us up the stairs, but I started in the railways 20 years before you, 71. I've been finished 16 years, but it ain't about me. I mean, it's a fantastic presentation. Your slide brought back memories of when your father took of winning Junction, because we went out as a technical team to mark out for 2 concrete bearer crossover roads to replace that junction. And guess what? The money wasn't there. So I just pulled the road out from that, so it never happened. The first concrete bearer we got up in this area was a little mill on the main line, about 39 miles north of Newcastle, and we did a blanketing scheme beforehand. We had all the ballast prepared, but we got that in loose super relaying with slew rails in 16 hours, and we opened the traffic. I mean, that doesn't sort of happen nowadays, but I can see why. Stuff is a lot more complicated. I wish I'd had some of this stuff when I was putting the layouts in. We've had switch diamonds up here as well. We'll put them in at Birmingham, and I've never been back since. So
You get that.
Maybe the chemicals in the air.
So in Manchester, they've had some nightmare junctions where they've constantly failed and not been able to fix them. And there's one, I can't remember which one it is, just south of Manchester, where one of the routes was closed for 2 or 3 months until they completely renewed the junction because it just failed that regularly and that catastrophically in the end. So some people have nightmares, and yet the likes of Colne Junction and Micklefield on TRU, I've never heard of a reported problem with those. So it might be how they're maintained is a big chunk of it, how well they're maintained.
Yeah.
So you just mentioned concrete, something I didn't mention because there was comment about composite bearers earlier. Concrete, obviously it doesn't rot, but it doesn't necessarily last longer because it corrodes. You lose the bottom corners, so you lose the ballast retention. So they actually fail in a different way. Although they don't rot, they actually fail quicker than a timber bearer, and they're also very, very harsh on the crossing. Timber bearers they're far more forgiving when it comes to crossings. So hence composite might be the way forward because they're a little bit more flexible than concrete. They're a little bit more sympathetic. So that will be interesting to see how the trials for those come out.
I'll just sort of continue on with the thanks and just observations as well. Newark, the best design of crossing there is obviously a bridge, and you do the cost benefit ratios. If your trains aren't going to stop at Newark on the main line, well, they can go Whiston by at 125, and also get more trains going from Nottingham to Lincoln without the conflict there. But that's for other people with big pockets to decide. Just going back to the Blythe and Tyne, or the Northumberland lines as it's called, I'm impressed with it must be a special that put in at Bedlington North Junction, which used to be 10 mile an hour and fall into bits, and was a TO going around with a track recorder. We used to run out of red paint before we even got there, all the dip joints, but that's now concrete layout, double junction, and 20 mile an hour.
I was going to say it's probably 20.
Yeah, so it must be a special, I think.
No, I think it's a fairly standard 56 though. It's an NR56 junction.
I must get off sometime when Bedlington Station's open. Let's have a look at it.
You can ask Roger Glenville if he actually turns up.
Oh, sure. I'll stop my waffle there now, but thank you very much. It's been a very detailed presentation, and I'm pleased I'm retired. So I'm sure I appreciate it in the usual way.
Thanks, Trevor. Thanks again, James, for your time, and I do hope you can come back and talk to us about Transpennine at some point.
Yeah, so Phil Kirkland had a choice of me doing double junctions or a presentation on transparent route upgrade. He made the right choice because the other presentation is 165 slides.
So there you go.
YouTube.
Yeah, so our next meeting will be Tuesday, the 4th of February, back here. PWI Junction track works on Nexus. And we've got Lee Stevens and Gareth Hudson from Smart Tracks presenting. So with that, thanks for coming. And hopefully students will get into the groove for the next meeting and we'll get them all there. Yeah.
Next meeting, trust us.
Yeah. Okay. Thanks everybody for coming and I'll bring the meeting to a close.
Thanks very much. I didn't realise I didn't have to deal with the questions there, Ed, the online questions.
That's okay, Manuel.